Okay, maybe I should quickly review. Okay, so it's like you know what are glitches. That means if you have a circuit and for some input combination, if one or more of the input changes, either from 0 to 1 or 1 to 0, then according to the logic function that is implemented by the circuit, let's consider two situations. One situation is the output was 0 and does not change for 0. This is we call a static 0 condition. This is the desired behavior, or it was 1 and it should have continued to remain 1. It should have continued to remain 1. This is called a static 1 condition. But this is at the output. That means even though input changes, one or more of the input changes, the output should, the desired behavior, the function states that the output is either static. I mean, let's consider only two conditions. Output is static at 0 and static at 1. But due to propagation delays or other types of delays also, due to propagation delay, this static behavior doesn't happen. Okay, so what might happen is that in this momentarily, in this static 1 situation, there may be a negative pulse for a small amount of time. Usually amounting to if tau is the propagation delay, this is only for a tau period of time. Similarly, in static 0, instead of staying static at 0, there is a momentarily positive pulse. And then it goes away. This is again maybe for a tau period of time. So these are glitches. We call a circuit to contain hazard if there is a potential for a glitch. Potential for a glitch means it's not that for all input combination and all input transitions such glitches will appear, but for some input combinations, some of the input combinations, this type of glitches may appear. Usually the problem with this type of glitches is that in a synchronous circuit, usually you don't have a problem because, okay, also we studied about that fundamental mode. That means the input change I mean after one input change, the second change doesn't happen till the output is stabilized. Okay, so these glitches are actually not stabilized. So once it gets back to a static 0 or static 1, we call it to be stabilized. So the fundamental mode, there will be only one input change till it stabilizes. So for synchronous circuit, if the stabilization time, the clock cycle is more than the stabilization time, there won't be any problem. But for asynchronous circuit, where we really don't have any clock cycle, as and when simultaneously when changes happen, so the output of this circuit may be the input to some other circuit. And these momentary glitches may cause undesired behavior for downstream circuits, may cause in asynchronous mode. Of course, in synchronous mode, is the clock width is less than this may still happen, but this tau is really small, so clock width is usually more than that. But in asynchronous, it's a problem. So we will see that this static 0 hazard and static 1 hazard. Let us see why this really happens. Okay, so the static 1 hazard. I'm just reviewing so that you can make just remember what is done. Static 1 hazard typically happens in a situation like this. So you have say a OR gate, and so this is I'm drawing an effective circuit. Let's say this is A, and then you have a NOT gate. Okay, so the output Y is A plus A bar. Output is A plus A bar. Why static one will happen? So output is A plus A bar means that I'll really explain. So this is actually maybe not a circuit that we encounter, but this is I'm just explaining. We'll see how we reduce to this circuit in a static one hazard situation. Okay, so what is the problem? So here you see that whatever may be the input, even if the input changes from 0 to 1 or 1 to 0, whatever, the output should always be 1. So it should always be static at 1 because it is A plus A bar. A plus A bar. It should always be 1, whatever be the transition on input. But the problem is this NOT gate has a delay of tau, say 2 nanosecond or something, has a delay of tau. This OR gate might also have a delay. So if we really look at the timing diagram, what happens is that, so let's say I have a 1 to 0 transition. I have a 1 to 0 transition. So this is 1. And so if we look at A, if A has a transition like this, because of the delay in, so this is A, because of the delay in NOT gate, 0 will appear here after some time. Okay, so rather 1 will appear here after some time. So this will become 1 after tau amount of delay. Okay, and now let us look at the output. Output was, let's say, initially 1, and then only for this period of time you can see that both were 0. So output is temporarily 0 here. In fact, this will not happen here. This gate will also have a delay. So this will not immediately happen here. This will start somewhere here. So not here, somewhere here. Usually the NOT gate and the OR gate will have the same delay. So this will happen here. And this will go to 0. Then afterward, when it comes back with some delay again, tau amount of delay again, this will be back to 1. So this is the glitch. Similar thing can happen for static 0. Static 0, it can happen in this kind of situation. A and A naught. Okay, so you have A over, which is should be equal to 0, and this is A plus A bar, which should be equal to 1. So on these transitions, this can happen. Okay, so one thing is clear: if we just had these two kind of circuit, this A plus A bar kind of circuit and A into A bar kind of circuit, we would have a static 1 fault because of this propagation delay. We would also have a static 0 fault because of this propagation delay again. Okay, now the question is that is it so that if we don't have this kind of circuit realization, we will not have an hazard? The thing is that even for 2-level circuits, let's say I have a 2-level circuit, I'm just writing down the expression. Let's say Y equal to BA. There are 3 inputs, say, and C A prime. Okay, so if we draw it as a circuit, it will be so let's say Y equal to BA plus C A prime. So if we draw it as a circuit, it will be A, B, C, and A prime. This is Y. Okay, so let's see if B is 1 only for this input combination and C is 1, then Y is nothing but A plus A prime. So you can potentially have a static 1 glitch. So there is a static 1 hazard. Okay, but this is only for this input combination. If B is 1 and C is 1, only then you will have it. You can check out that if you have other input combination, then this will not happen. And this will not happen. Okay, this will exactly not happen. And similar thing you can have for a static 0 hazard. So for some input conditions, there may be a glitch. So we say that this circuit contains a hazard. So essentially, the way we can detect whether such a static 1 hazard exists or not is just whatever be your circuit. Let's say it's a 2-level realization, it's an AND OR realization, sum of product realization. Then we see if for some input combination of the variables, such a plus A bar structure appears or not. Such a plus A bar structure appears or not. This condition is very easy to check by using Karnaugh maps. This is very easy to check using Karnaugh map. All you need to do is the following. You suppose you have your Karnaugh map and you have some minterms. Let's say you have some minterms like this. Okay, let's say these are the 3 minterms. What we will do is that we'll just check, we just need to check if in the Karnaugh map there are 2 adjacent minterms, note one thing that this is a property of the realization. Whether hazard will be there or not is a property of the realization. It's a property of the realization that we have, not on the technology, not whether you use CMOS or TTL or anything, but on the realization that we have, circuit that we have. So let's say this realization, this BA plus CA bar realization, I don't know whether it matches with this. Maybe I should have done. But anyway, let me explain. I think you have already covered this. So you look at 2 adjacent 1, and suppose this realization corresponds to these 2 prime implicants. It has these 2 prime implicants. Okay, so if there is an adjacent 1 which is not covered by a common product term, common prime implicant, common implicant, which is not covered by a common product term, then we say that there might be a hazard. So if we have a situation like this, which is covered by these 3, these and these and these, so this is an adjacent term, and there is no common product term which is covering them. There are 2 different product terms covering each of them. Then there is a potential for a hazard. Okay, so it's very easy to check. You draw the K map, take all your minterms, look at adjacent minterms. If there is a pair of adjacent minterms, logically adjacent, so you can roll around, wrap around those also. If there are 2 logically adjacent minterms and there is no product term covering both the adjacent minterms, then there is a potential for a hazard. Why? Because then for some input combination, for other input, for some combination of the other input, this will lead to a plus A bar kind of situation. This will lead to a plus A bar kind of situation. Okay, and you can have a static 1 hazard. How to remove the static 1 hazard? Very easy. Add redundancy. Add an additional product term. So add an additional product term. This would mean that, well, maybe something like this. You can add an additional product term, additional AND gate you add, and you add it to the OR gate. A third input, have it as a third input of the OR gate. Okay, and this you can actually check out that if the such thing is there. So see why this is happening, because one of this is becoming the forcing input. Okay, so moment you have this, it's becoming the forcing input of the OR gate. Moment you have a third input, one of them will not be the forcing input. You need a third input. Okay, so this can be avoided. Similarly, how can you check a static zero hazard? So basically, you are avoiding this hazard by introducing redundancy, introducing unnecessary AND gates, which are sacrificing your cost, but you are gaining this hazard-free operation. Okay, so static zero hazards occur due to this kind of situation. When this can happen for some combination of inputs, say like this. When B is 1 and C is 1, this can happen. This is also very easy to check using Karnaugh maps. So what you actually do is that instead of looking at the min terms, you look at the max terms. Look at the zeros. You look at the zeros. And the rule is same. If there are two adjacent zeros, which are not covered by a same sum term, which are not covered by a common sum term. So if these are two adjacent zeros, but there is no sum term like this in the circuit, in the realization. Maybe the realization didn't have it because it was not necessary. These were covered by other sum terms, max terms. So, other sum expression. So, what you do is that you again introduce an additional sum term to cover these two. Okay, this would again mean, so this is a product of sum. So it is an OR AND circuit. So the second level AND will have 3 inputs, more inputs than necessary. We will have a redundant input, and you have a redundant OR in the first level. Okay, so this is how we avoid, and this can easily be formalized. So I am just giving an sort of circuit-based understanding of this thing, but you can easily, of course, mathematically write it down using the cubes and necessary cubes, required cubes, and so on. Okay, so then you can have dynamic hazards. Okay, so what happens in the static hazard is that the output was supposed to be static at, let's say, 1, and there was a negative pulse momentarily. Note that all these hazards are if the next circuit waits enough long time for it to stabilize, then hazards would not have been a problem. If it is so that the subsequent circuits are sensitive to these glitches, only then the problem can happen. So usually by synchronization, you can remove such glitches. Or rather, glitches can have no effect. They will not propagate. All right. So so this is a one single thing. But what this is static hazard. So you can think of it like this. So suppose from 0 it's going to 1, then there will be a momentarily, so there is a momentary glitch, then it happens. So what happens in dynamic hazard is that there may be multiple such pulses before it stabilizes. Okay, so there can be multiple such glitches. All right, so a dynamic hazard. So again, I am telling you that, see, these are all property of the realizations. These are all property how you implement the function which you use to implement the input output. Okay, the Karnaugh map. So if you have redundancy, you can avoid this. If you don't have redundancy, this can. So these are properties of the realization, or the realization the function with which you are realizing. Okay. So in dynamic hazard, usually it's a situation like this. Or for some input, so there are, let's say there are other inputs B, C, D. For some combination of B, C, D, if the function reduces to this form, then you can have a dynamic hazard. You can also think of this as combination of multiple static hazards. These are combination of multiple static hazards. Okay, so if the function reduces to something of this form, then you can have a dynamic hazard. Usually, if we look at the circuit, if you draw the multi-level, if you draw the realization using and sum of product or product of sum, which are so the dynamic hazards can only happen when it is a 3-level circuit. So these are all 2-level circuits, but this can only happen when there is a 3-level. So there is an easy way to check. There is a necessary condition for dynamic hazards to happen. First of all, it has to be a 3-level circuit, which we will see is implied. So sum of the input, there should be at least 3 paths from input to output. 3 different paths from input to output. So if you follow the data path from input to output, say any one of the input to output, so at least one of the input should have 3 or more number of possible paths from input to output. If you draw the circuit, only then a dynamic hazard can happen. Okay, we can easily see that this kind of situation can only happen in such case, because you see these are 3 possible paths. Okay, and in a 2-level circuit, you cannot have such things, so you need a 3-level circuit. Okay, so they can so avoiding dynamic hazards are more difficult, but you can do them. You can still draw the Karnaugh map, and you can do this. All right, so these are for single input change. These are for single input change. So this is what single input change what I talked about. You look at transition between some input combination and then generate momentous output. So these are some of the concepts. Let me quickly review. A transition cube is the set of all minterms that can be, transition cube M1, M2 is set of all minterms that can be did starting from M1 ending at M2. Required cube is a transition cube that must be included into one of the product in the sum of product realization in order to get up static 1 logic hazard. So as I explained here, so these are kind of required cubes. The redundant, this AND block is a required cube. This redundant AND is a required cube, which you need to avoid the hazard. Okay, so this is a required, this dashed line is a required cube. So this is also the same thing we already discussed. Now let us go to multi-input change. So several inputs can change values, but monotonically. Monotonically in the sense that you have a step-like function. You go from 0 to 1 or 1 to 0. You have a step-like change. You don't have a pulse. You don't have a train of pulse-like change. You don't have 0 to 1, then 1 to 0, and 0 to 1. You don't have a train of pulse-like change. You only have a step-like change. You cannot have this kind of change, or maybe this kind of change also. So this is non-monotonic. This is monotonic. Okay, so in the process of this, so even in the process of this monotonic change, but the additional thing here is that more than one input can change at a time. So it's the MIC scenario. More than one input can change at a time. All right. So because of this monotonic change in one or more of the input, if the output function changes more than once, so ideally the output function should have changed because of this monotonic change in hazard. As you know, for monotonic change in input, there should be a monotonic change in output. So the output should have been transitioned and then stabilized immediately forever for the next, till the next change in input. Okay, it should have been monotonic, but it's not. It changes value once and then maybe again and then maybe once. So maybe it changes value more than once. Even though the input has changed value only once, we said it is a function hazard. Okay, we say this is a function hazard. Why can function hazard happen? The function hazard can happen because say look at a circuit like this. Okay, so if these are the input combinations, and then maybe x prime is changing, so basically x is changing and say z is changing, y is static, let's say y is static, x and z are changing, so accordingly x prime z prime are also changing. So if we look at the output of this AND gate, some of the changes, because there is a all these AND gates are not uniform, there may be a variation in delay in each of them. One may have the highest delay, one may have the least delay, so there may be a variation in propagation delay. So this output of the AND gates may change at different values of delay. Definitely they are not instantaneous. All AND gates will have a delay. These are inertial delays in the sense that there are resistance and capacitances, whatever technology you have, and they cause an inertial delay. They hold back the circuit due to RC inertia. So these output changes are not synchronous. They are not at the same time. They are with different delays. And if that comes in the as input of the OR gate, naturally in the output there may be glitches. There may be glitches in the output. Okay, so this can happen. This can happen due to other thing also. Maybe this falling transition is faster than the rising transition. So this is faster than the rising transition. So all this can happen. So so you can naturally see that if you have multiple inputs changing and there are multiple AND gates as at input, again I am considering a two-level circuit. I am not considering a dynamic hazard. I am considering static hazards only. So then you can have glitches. I think that is obvious. If you work out the timing diagram with some varying delay among these AND gates, you will see that there will be glitches. Okay, so as we have done in the last class, let's represent it by like this. So these are the transitions. This is the transition on. This is the transition on Z. Yeah, this is the transition on Z, 0 to 1, transition on Z, and this is the transition on X. It is a. All right, this is a transition. No, this is something different. Let me see. Okay, so how do you? So you see, so you look at each of the transitions. So this is a transition. Okay, this is a transition. What you do? So and what is the transition cube? So this will be the transition cube. Everything that is reachable. So what you have to do? You have to cover this transition cube with an additional gate to get rid of the static hazard. So that's the standard way we studied in the case of static one hazards. You introduce an additional product term, an AND term, additional AND gate to cover these two, which is redundant, which was not required. So this is just as in the single input change case to cover this. This is the additional gate you have. Okay. So there are some necessary conditions so this is for single. Let's see for the multiple input case what are the necessary conditions. So each of so you can break down a MIC into several SICs, and this individual SIC, let us consider them as sub transitions. So if you have the entire chain for a MIC, one of the variables change, we call that as a sub transition. So what is the necessary condition for a MIC to be hazard free? Either static 0 or static 1. Make sure each of the 1-1 sub transition is hazard free. How do you do this? Include all these sub transition into some product. Introduce an and get for each of these sub transitions. For each of these sub transitions, include an and get. Okay. So basically all these sub transitions which have to be covered are called the required cubes in the dynamic transition. So for the dynamic transition, this will be the required cubes. All right. So another thing has to be ensured is that none of the AND gates. So this is an AND kind of structure. So another thing you have to ensure is that during this multi-input transition, none of these AND gates should turn on. But you see this first gate, G1 gate, sorry, this G1 gate can turn on because this WZ intersects. So you have to avoid this kind of thing. So these are called illegal intersections. These are called illegal intersections. Okay. Okay, so what you have to do is you have to disallow and privileged cube. You have seen that it is this dynamic transition is a privileged cube. So you have to avoid all illegal intersections with the privileged cubes. You have to avoid all illegal intersections. So how do you do that? You replace WZ by WY prime Z. You can see if you do that, this will be. So you add an additional input to this G1. Okay. So all 1-1 transitions must be completely covered. All 0-0 transitions are harmless. For all 1-0 to 0-1 transition, ensure that every product term that intersects with this transition cube also contains the start and the end point. For start for 1-0, end for 0-1. They should contain. Okay, so you have a kind of implicant which is called a DHF implicant, dynamic hazard free implicant. Okay, a dynamic hazard free implicant is, if you look at any of these dynamic transitions, if none of these implicants illegally intersects any of these dynamic transitions, then you call it a DHF implicant. A DHF prime implicant naturally is a DHF implicant not properly contained in any other prime implicant. So to find out this, so all you need to do is that, so earlier I told simply you just need required cubes. You just need a covering product term, add an additional AND gate. But here you have to look at something more for MIC. You have to look at DHF implicants, dynamic hazard-free implicants. The problem of finding dynamic hazard-free implicant requires a Quinn-McCluskey type of minimization. So here is an example which you can see. So all this, if you look at this chart, this is a MIC in the sense that this transition, so this transition, this transition, this transition, and all this MIC transition can happen. These arrows represent the MIC transition. All the in the first figure A, all the cubes that we have drawn are required cubes. Because you see they are covering the adjacent things, they are all required cubes. In the B, with the dash term, we show the privileged cubes. Okay, and in C, all the prime implicants with no illegal intersections are shown. All the prime, these prime implicants, they are DHF, they do not have an illegal intersection. This is an example where you have an illegal intersection. So what we do, because we take into prime implicants with no illegal intersection, and from that we find out the dynamic hazard-free prime implicants. So these are the dynamic hazard-free prime implicants. You just overlay this on this and you can find this. Okay, and this is the final hazard-free sum of product. So this you can what you do is that you write the DHF prime implicants and you find out the required cube. So just by the similar method, all this row dominance, column dominance, you find out the final sum of product form. Okay, and this will give you a hazard-free sum of product. Okay, so I think that's it. Let us stop. Most probably CRM will take a class today. I'll confirm from CRM. Most probably CRM will take a class today. He will